Okay, good day. This is Math 140 College Algebra. I'm Professor McCulley, and this is Lesson 4.6 on the rational root theorem. Let's get right to it. Today we're going to use the rational root test to find zeros of a polynomial. We're going to use Decartes' rule of signs to find the number and type of zeros of polynomials, and we're going to find upper and lower bounds of polynomials. The rational root test: if a polynomial f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus all the way down to a sub 2 times x squared plus a sub 1 x plus a sub 0 has integer coefficients. So right off the bat, they're saying that each of these coefficients here have to have integer coefficients. Then every rational zero, and a rational zero, R-A-T-I-O, the first 5 letters, spells ratio. So every fractional type 0 has the form P over Q, where P and Q have no common factors other than 1, and P is a factor of the constant term. Remember, the constant term is always going to be a sub 0, and Q is a factor of the leading coefficient. The leading coefficient is always the coefficient of the highest power. Let's look at an example. Using f of x equals 2x to the third minus 3x squared minus 11x plus 6. Make a list of all the possible rational zeros. Use technology to make a guess for the rational zeros, and then verify your guesses with synthetic substitution. Okay, so first thing for our list of possible rational zeros, if we go back to this rational zero test, we're talking about P being a factor of the constant term. The constant term is always that last term that has no variable, and a factor of the leading coefficient. So we've got to factor this constant term and this leading coefficient. So let's do that. Our constant term, so our values for P are going to be factors, and just so that we can see it, 6 and P are going to be our factors for that. So we have all the possible integer factors of 6. So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are all of the integer factors of 6. Now we also need to find Q, and Q is the leading coefficient, and so the highest degree is 3, so our leading coefficient is 2, so we're going to find all of the factors of 2. That's a little bit shorter of a list, plus or minus 1 or plus or minus 2. The list of all possible rational zeros will be P over Q. So remember, we're only going P over Q, not Q over P, just P over Q. So all of this list will be over 1, and then all of that list will be over 2, and that is it. So anything over 1 is just going to be that value, so I'm going to repeat the P list first, and you're probably always going to start with that. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, because we go 1 over 1, 2 over 1, 3 over 1, 6 over 1. And then we have to go all of these numbers over 2 as well. But some of them we are not going to need to do. So 1 over 2, we don't have that yet, so plus or minus 1/2. 2 over 1 is 2, and we already have 2, so we don't have to write that one. 3 over 2, though, is 3/2, and we don't have that one. And then 6 over 2 is 3, and we already have that one. So we are done. This is our answer to part A. Now part B says, use technology to make a guess of the rational zero. So let's pull up our graphing calculator. So I have already entered our equation into the graphing calculator here. So 2x to the third minus 3x squared minus 11x plus 6. I'm going to hit graph. Here are our zeros. It looks to me like -2 is a 0, and 1, 2, 3 is a 0. So we're going to try -2 and 3, and then that one looks like it might be a fractional, but since it's a third degree polynomial, if I divide out 2 whole number ones, that last one will be easy. So I'm going to start with -2, I'm going to try -3 and see what that last one is. So let's start by listing the coefficients, and so I'm in B now. My guesses are x equals -2, 3, and I'm going to guess a half. That's in there. It looks like it was in between. And so I'm going to put my coefficients. So it was 2, -3, -11, and then 6. And we'll first start by dividing out -2. So bring down my 2 there. 2 times -2 gives me -4. Add these two, I get -7. Times -2 is +14. That'll give me a +3. That'll give me -6, and I get my 0. So -2 was a good guess. Let's do 3, see how I did. Bring down the 2. 2 times 3 is 6 plus -7 gives me 1. -1 times 3 gives me -3. That'll give me a 0. Since I've divided out x plus 2 and x minus 3, and we started with a third degree polynomial, what's left is going to be 2x minus 1. And so what I can do is I can set that equal to 0. And we can say 2x equal to 1, x equal to a half. So for part C, we have done all of our verification. The zeros are x equal to -2, 3, and 1/2. All right. Descartes' rule of signs. Let f of x be that polynomial. I won't do that again. Let be a polynomial with real coefficients and a sub 0 not equal to 0. So you have to have a constant term for this to work. If it doesn't have a constant term, you should divide out an x first. All right. And what that means is that one of your zeros is actually 0. The number of positive real zeros of f is either equal to the number of sign changes of f of x or less than a number by an even integer. So you count the number of sign changes and then you reduce that by even values. So if you count 5 sign changes, your number of positive real zeros are going to be 5, 3, or 1. If you count 4 sign changes, your values will be 4, 2, or 0. Count the number less than that by an even number. To find the number of negative real zeros, you have to do a little bit more first. The first thing you got to do is you have to plug in -x and then evaluate that. And once you evaluate that, count the number of sign changes, and then the same thing. It's less than that by an even number. So let's look at an example here. It says, find the number of possible positive real zeros. So for part A, I come up to this expression here, and my constant term, I have one. And so to find the number of possible positive real zeros, I'm going to count the number of sign changes. Okay, so it starts off positive. This one is positive. So that's not here. I have my first sign change. Then it stays negative, and then it changes to positive again. So here I have 2 sign changes. So the number of possible positive real zeros is either 2, because I have 2 sign changes, or less than that by an even number, or 0. That's it. Now for part B, I have to plug in f of -x first. So I have to plug that in. So let's do that. I got 3 times -x to the 4th plus 11 times -x to the 3rd minus 16 times -x squared minus 44 times -x plus 16. All right. So the reason that you have to plug in -x is because if you take a negative to the 4th power, or an even power for that matter, squared too is going to work. Negative times itself 4 times, or negative times itself twice, is going to be a positive number. So this term is not going to change even though I plugged in -x. This term though, because when you multiply a negative number by itself 3 times, produces a negative number, that sign is going to change. So when I take -x to the 4th, I get x to the 4th. This stays 3x to the 4th. When I take -x to the 3rd, I get -x to the 3rd times positive 11. It's going to give me -11x to the 3rd. -x squared is going to give me positive x. So that term will not change. Negative 44 times negative x is positive 44, so that term will change. And then I have my positive 16. So it starts positive and then changes to positive. So there's my first sign change. Then from negative to a negative is still negative. From negative to a positive, there's my second sign change. And then positive to a positive, I only have positive values. So the number of possible negative real zeros is also either 2 or 0. And there's my part B. Now, this thing has to have 4 zeros. It looks like there's a possibility that you could have 2 positive and 2 negative, or there's also a possibility that there are no real zeros. They could all be imaginary, or you could have 2 positive zeros and 2 imaginary zeros, or you could have 2 negative zeros and 2 imaginary zeros. So there's lots of combinations still, even though we know that there's that many possible zeros. Finally, upper and lower bounds. Upper and lower bounds are just used to limit the number of possible choices using the graphing calculator. You don't necessarily need to know upper and lower bounds, but I am adding upper and lower bounds to this lesson because last year it was on the final exam. And basically what upper and lower bounds means is that if you go through and you make a choice and you try and see if one of your guesses is an upper or lower bound, let's say you don't get a 0 out, the upper bound says if each of the value is either positive or 0, then C is an upper bound for the real zeros of F, which just means you don't try anything above that number. And then if you go and you do your synthetic division, each number in the last row is alternatively positive and negative. So if the sign switch from positive to negative, then C is a lower bound and you don't try anything lower than that because there are no zeros beneath that. Now the last thing you need to know, even though we're talking upper and lower bound, and usually when you say bound, you're talking about boundaries. You can have multiple upper bounds and multiple lower bounds. All right, you wouldn't necessarily try anything above or below that. So what does that look like? It says use synthetic division to verify the lower and upper bounds for the given functions below. So they're telling us in this direction that the upper bound is 4. So when I plug in 4, I shouldn't get 0 out, but my coefficients in the quotient should all be positive. So if I go 2, negative 3, negative 12, and then 8, and we were to try to see if 4 divides that. I bring down the 2, 2 times 4 is 8, 8 and negative 3 is 5, 5 times 4 is 20, 20 and negative 12 is 8, 8 times 4 is 32, I get 40. Note, all positive results. Thus, 4 is an upper bound. All right? And so we know, what is the conclusion? We know that there is not going to be any 0 of this polynomial that's bigger than 4. All right? All of the zeros for this polynomial must be smaller than 4. All right, lower bound, negative 3. So let's do the same thing. 2, negative 3, negative 12, and 8. And so we're going to plug in negative 3 here. I bring down my 2. 2 times negative 3 is negative 6. Negative 6 and negative 3 is negative 9. Negative 9 times negative 3 is going to be positive 18. 18 and negative 12 is going to be positive 6. And then 6 times negative 3 is negative 18. And I will get negative 10 there. And notice, alternates positive and negative. Thus, -3 is a lower bound. And that tells us that there is no value for x less than -3 that will be a 0 for this function. Well, that's all I got for today, folks. So, the Marvel fun fact of the day, Agent Jimmy Woo produces his identification with a flick of the wrist, and the card appearing in his hand as if by magic. This is a reference to the character's first appearance in Ant-Man and the Wasp in 2018, where he is shown to be instantly fascinated by Scott Lang's mastery of close-up magic, but completely unable to do any tricks himself. So in Ant-Man, saw the trick, wants to know how to do it, has been practicing it. Beginning of WandaVision, there he is, able to do the magic card trick. Well, that's all I got for today, folks. Have a good day.